Hello, good morning to all of you. Myself, Dr. ATUL Kumar Srivastava, Assistant Professor, Department of Chemistry, Magadha University, Bodh Gaya. The today's topic of my lecture is aromaticity. We all know that aromaticity is a very vast topic which comprises the aromatic compounds, non-aromatic compounds, anti-aromatic compounds, and the homoaromatic compounds. In this lecture, we try to understand that what are the factors by which we can identify that a particular compound is either aromatic, non-aromatic, or anti-aromatic or homoaromatic. Let's move. What are the conditions for the aromaticity? For a molecule to be aromatic, one looks for following three conditions. The condition number one, the molecule must be cyclic and planar. The condition number two, the molecule must follow Haeckel's rule of aromaticity, that is, it has 4n plus 2 pi electrons where n is equal to 0, 1, 2, 3, etc. anything. And number three, all the 4n plus 2 pi electrons must be delocalized above and below to the plane of the ring. One of the simplest and finest example of aromatic compound is benzene. The molecular formula of benzene is C6H6. It has 3 pi bonds which are conjugated. The molecule of benzene is cyclic and planar. It has 6 pi electrons. That means according to the Haeckel's rule, it follows the Haeckel's rule. 4n plus 2 is equal to 6, therefore n is equal to 1. That means the benzene molecule follow the Haeckel's rule of aromaticity. And the last, all the 6 pi electrons in the benzene are delocalized above and below to the plane of the ring. It has been very clearly shown in this molecular orbital of the picture of benzene, where the 6 p orbitals in which the delocalized pi molecular orbital are shown above and below to the plane of the ring. Now, what are the characteristics of aromatic compounds? The first characteristic is it must have delocalized conjugated system. Without delocalized conjugated system, any molecule cannot be called it is a aromatic compound. Then number two, the molecule must have the coplanar structure with all the contributing atom in the same plane. And number three, and the most important, the number of pi delocalized electron must be equal to the number given by the Haeckel's, that is 4n plus 2, where n is equal to either it may be 0, 1, 2, 3, and so on. This rule is known as Haeckel's rule. This is the Haeckel rule. We all know that according to the Haeckel, any molecule having 4n plus 2 delocalized pi electrons, it may be called aromatic. But the molecule must be planar, monocyclic, with continuous system of p orbitals, 4n plus 2 pi electrons, where n is equal to 0, 1, 2, 3. Aromatic compounds always shows resonance stabilization. In this slide, I am just comparing the difference between the aromatic compound, anti-aromatic compound, and the non-aromatic compound. Aromatic compound must be cyclic, planar, conjugated, having the 4n plus 2 pi electrons. Where in the case of anti-aromatic compounds, it is cyclic, planar, completely conjugated, having only 4n pi electrons. This is the marginal difference between the aromatic compound and the anti-aromatic compound. The aromatic compound have 4n plus 2 pi electrons, whereas the anti-aromatic compounds have 4n pi electrons. The aromatic compound stabilizes the system, whereas the anti-aromatic compound destabilizes the system. As per the definition, we can say that the anti-aromatic compounds are those compounds which are destabilized by a closed loop of pi electrons. The third category is non-aromatic compounds. That means the compound that lacks one or the following requirement for aromaticity. that is either being cyclic, planar, and completely conjugated. That means any particular compound, if it is cyclic but not planar, it may be called as non-aromatic. If it is cyclic, planar, but neither follow 4n plus 2 system nor follow 4n pi system, then it also may be called as not aromatic compounds. In this slide, there are 4 examples. The first one is aromatic, that is called benzene. The second one is cyclobutadiene, that is anti-aromatic. The third one is cyclooctatetraene in the planar form, and the fourth one is the cyclooctatetraene in the tub-shaped form. The planar form is anti-aromatic and the tub-shaped form is non-aromatic. It is very clear that the cyclooctatetraene is found in tub-shaped form, which has been proved by experiments that it is not a planar form, it is a tub-shaped form. That is why the cyclooctatetraene, in spite of having 8 pi electrons, it follows non-aromatic system and behaves like a conjugated polyene, because the cyclooctatetraene is a tub-shaped form which is not planar form. Another example is cycloheptatriene. In cycloheptatriene, there is a 3 pi bond which are conjugated, and one carbon atom is sp3 hybridized. That is, it is a non-planar molecule, cyclic but non-planar molecule. That is why the cycloheptatriene is non-aromatic compound. In another picture, that is cycloheptatrienyl cation, a positive charge makes the carbon atom planar. That is why it becomes aromatic, because it has 6 pi electron, which is the number of Huckel's rule system. So cycloheptatriene is non-aromatic and the cycloheptatrienyl cation is aromatic. Another example is cycloheptatrienyl anion. It is a cyclic planar molecule having 8 pi electron system. We all know that the 8 pi electron system is not in the form of 4n plus 2, it follows 4n pi. That is why cycloheptatrienyl anion is anti-aromatic compound. So in this example, the 7-membered ring, first one is neutral, the second one is cationic form, and the third one is in anionic form. The neutral form is non-aromatic, the cationic form is aromatic, and the anionic form is anti-aromatic. If we consider the stability of these 3 compounds, so what we found, the aromatic compounds are the most stable compounds. That is why the cycloheptatrienyl cation will be the most stable, whereas the anti-aromatic compounds are the least stable. Even they are less stable than the non-aromatic compound. That is why the cycloheptatrienyl anion will be the least stable compound. Another set of example, the first one is cyclopentadiene, the second one is the cyclopentadienyl cation, and this third one is cyclopentadienyl anion. The cyclopentadiene, that is the neutral form, is non-aromatic because one of the carbon atom is sp3 hybridized. That is why the molecule is non-planar. In the second, the cyclopentadienyl cation, it is cyclic, it is planar, but having 4 pi electron, which is the number of 4n pi system. That is, it is anti-aromatic. And the third one is cyclopentadienyl anion, which is cyclic, planar, having 6 pi electrons. That means it follows 4n plus 2 Huckel's rule. That is why the cyclopentadiene anion, which is oftenly called as CPT anion, is aromatic in nature. If we compare the stability of these 3, what we found, the cyclopentadiene anion being aromatic is most stable, and the cyclopentadienyl cation being anti-aromatic is least stable. In this slide, there are some aromatic heterocyclic compound. Heterocyclic compounds may be aromatic or may not be aromatic, but in this slide, the pyridine, pyrrole, furan, and thiophene, all these 4 compounds are aromatic in nature. Thank you.